Hey guys, what's up? Welcome to Some Good Science, where some good science is better than none. In case you're wondering if I'm wearing the same shirt for a third day in a row, you're absolutely correct. That's because it's a Star Wars periodic table, and it was a really great week for Star Wars puns. Um, May the Fourth be with you. Juan Solo celebrating Cinco de Mayo and May 4th. And in chemistry, we're going to be talking about atoms in the periodic table. So let's get started. All right, so we started off with talking about in your notes, you'll see we're talking about how are atoms and molecules related. We're going to distinguish between atoms and molecules. So let's see what you know first. If we were writing notes, we would copy this down. Feel free to do so if you want. In our previous lesson, we learned that the pencil is made up of matter. If you look closely at the tip of this pencil, you will see that it is made of the mineral we are already familiar with, graphite. Graphite is composed of carbon atoms. So if you look really, really closely at this picture of graphite, then it's made up of atoms. You can't see it though. So they're really small, and atoms always contain, atoms contain protons, neutrons, and electrons. There's the activity sheet we'd be filling out. How big is an atom? If you guys have not checked this out, you have got to check it out. I think I'm actually going to save this fun part for last, and let's just kind of get through the basics first, right? All right, first, atom, smallest part of matter, consisting protons, which are positive, neutrons, which are neutral, and electrons, which are negatively charged. Atoms have three basic parts. There you go. In the nucleus, you'll have your protons and your neutrons, and orbiting around them are the smaller electrons. Elements consist of two or more of the same exact atom. You can't break it down into any simpler parts. Okay, so the periodic table is arranged in order of their atomic size. Molecules consist of two or more elements chemically bonded together. Both elements bonded can be the same or different. In the animation, above, two nitrogen atoms, nitrogen plus nitrogen will equal nitrogen 2, making one nitrogen molecule. So if you have oxygen plus oxygen, that'll equal oxygen 2. So again, it's just the same elements, but when you have more than one of the same element, then you have a molecule. Okay, so next we'll talk about applying those atoms, elements, molecules to the law of conservation of matter. Okay, so in this next slide, you have a chemical formula, and it's a representation of substance using symbols for its essential elements. So here you have one atom of sodium, abbreviated as Na, and then you have two chlorine atoms, so that's why you have the little 2 next to it. And sodium by itself and chlorine by itself is very dangerous. In fact, I'll show you right here. You can look it up. The sodium element is actually right here. Very combustible solid and can lead to eye burns for real. In some severe cases, sodium is also called digestive tract and respiratory tract burns. So by itself, you don't want to touch it whatsoever. You can get symptoms like cough, sore throat, shortness of breath, and so on and so on. Now, chlorine by itself is something that you've also used in pools, and if you have too much of it, it's very dangerous. It produces like a gas, and has been used also, unfortunately, for some chemical weapons. So down here, you could see it too, that health dangers, very reactive to the human body, irritates eyes, skin, throat, and can cause permanent lung damage. But if you combine these two elements together, and then you can get salt, as you can see right there. If you combine them, they neutralize each other, and it produces sodium chloride. So beneficial for us for table salt. So a chemical formula represents in symbols and numbers the amount of atoms in a specific type of matter. Another example is you can see right here, we have the H2O, or the water molecule. You can see that there's just 2 hydrogen atoms and the 1 oxygen atom, therefore producing water. And if I were to go on here and talk to you a little bit more about conserving matter, the law of conservation. Well, what does that mean, right? If you have like a combination of these atoms, do they change or do they become something else? So in this one right here, you'll have this is a methane molecule right here. You have 1 carbon and you have 4 hydrogens. And if you were to take that molecule and combine it with 2 oxygens, then you're going to get a product. Here you'll have then carbon dioxide and you'll have 2 water molecules. So the number 2 here means that you have a total of 4 hydrogen atoms and 2 oxygens. And they balance each other out too. You could see here the reactants and the products too. You'll have 1 carbon and you'll still over here on this side, you'll have 1 carbon if you were to combine these to turn them into this product. And you still have 4 hydrogen atoms here and you still have 4 hydrogen over here too. So you have initially 2 hydrogen atoms and then the 2 in front of it means you have a total of 4. And same thing with the oxygen. Another way you can look at it too is, actually I'll go right here. Here's another way you can look at it, like if you were to put it like on a scale. This is using a little something different though, but this is what we had before, where we had methane and water molecules and oxygen and combining, and it's just another way to lay it out. In this one, you have an unbalanced equation. Oh, this sucks. Law of conservation. Law of conservation of matter. Here's another good example where you have 2, or a clear example of the previous page. You have 2 hydrogen atoms. You have, H2. So this is H2 and another H2. So you have a couple of H2 molecules. Right? Over here, you have 1 molecule of oxygen. You have 2 of the oxygen atoms though. Right? So if you react these together, then you get the product of water molecule. Okay? You could see that you still have the same number of oxygens over here, and you still have the same number of hydrogen atoms over here. Okay, still, so therefore, energy is neither lost or destroyed; it just changes its form. That's it. And you'll hear that a lot when you get into high school too. Okay, so let's actually go to the website. If you click on this link, like I said way in the beginning, and it's accessible in your notes, Scale of the Universe is pretty fun. Okay, so when you click on and you hit start, you can listen to this fancy music if you want. But I don't really want to hear that. And you start off with like the size of a human, and you got this giant earthworm, just like blows my mind away. It's pretty big. I wouldn't want to see one of those. And you can actually, here's your sliding scale, and you could like zoom in closer and closer and closer. And you can see a basketball is smaller than a human, and a hummingbird is smaller than the basketball. A shrew is even smaller, right? And then you can get like really small. It gets pretty cool. And this stuff is like, all right, yeah, I know all that stuff is smaller. Fast marble, microwave wavelength. All right. What else we got? Sleet, ant. And then let's see, bacteria. So I saw a couple of things here that's pretty cool. Oh, amoeba. Oh, wait, what's going on? All right, so the length of, and over here is your scientific notation too. So the thickness of paper, the human hair is not quite as thick, all right? So it's smaller than the width of a paper. Human eggs cell is very small, even smaller than the width of your hair. And then you get into parts of the cell that you learned last year in 7th grade science. Mist droplet, there's an idea, you talk about like coronavirus droplets being spread around, get an idea of how small we're actually talking about. and the virus being on that mist molecule droplet. I'll show you that in a little bit too. You get into the cell nucleus, the red blood cells, chloroplast. The parts of a cell are really small. Red wavelength is larger than the violet wavelength. We talked about the sizes of these wavelengths last semester. Your viruses are even smaller. And this guy right here kind of looks like our coronavirus coming up, right? That's how small viruses can be on that droplet. And then if you get even smaller, I'm going to zoom in a little bit more. DNA, even smaller. And it's going to get all the way down. So again, we're not even at the size of an atom yet. All right, right here. So here you have a carbon atom. Carbon atom has 6 electrons orbiting around the nucleus. And inside the nucleus, it has 6 protons as well as neutrons. Now, if you were to, over here, you'll see that we have a combination of some, atoms. This one right here by itself is actually hydrogen. And it kind of, you have 2 hydrogens, and over here you have an oxygen atom in the middle. Kind of looks like Mickey Mouse, doesn't it? Mickey Mouse ears. Okay, get a little bit smaller. There you can see your hydrogen is small, helium small as well, and the difference between hydrogen atom and helium are the number of protons in it. And usually the number of electrons floating around that atom is equivalent to the number of protons inside that nucleus. So if you have 1 electron orbiting around the nucleus, then it likely has just 1 proton inside the nucleus. This one has 2, so therefore we know it's helium, and there's 2 electrons and 2 protons inside of it, as well as a couple of neutrons as well. Just get a little bit smaller, X-rays are even smaller. Right? You can get really, really small, and you could get even smaller if you want to. Okay, but I actually think going the opposite way is way more fun. The bigger the better, right? Show you a couple things. All right, let's go. I'm on, Mike. All right, check it out. So there's the size of an average human. Okay, check this out. You got a giraffe, you got a T-Rex. Check out this desert cactus. It's bigger than a T-Rex. It's so big. Dinosaur's even bigger. Boeing jet's bigger than your largest dinosaur here on this. And your redwood trees are the tallest trees on the planet, which are about the size of the Statue of Liberty. Titanic's even bigger. Great Pyramids of Giza, the Hoover Dam, Half Dome in California, in Yosemite National Park, is really big. Angel Falls. Ayers Rock in Australia. Check this out. Central Park is even bigger. Halley's Comet's big. I should have known that, right? I forget these things. What do we got? Rhode Island, West Virginia. So they need, size of bigger states, bigger countries, planets. Check this out, though. This is really cool. Talk about Jupiter's four large moons: Callisto, Ganymede, Europa, and Io. Right? These guys are the 4 moons that you can, if you have a good pair of binoculars, you could definitely see them revolving around Jupiter. And just to give you an idea, obviously some of Jupiter's moons are bigger than Pluto and Mercury as well, and our own moon. And if you were to put the United States on the moon, for example, it would take up most of the moon's surface. Let's get bigger. Some of our planets, the Jovian gas planets, are bigger than Earth, of course. And then we get into some of the stars that we talked about last semester too. Proxima Centauri is a small red dwarf star. Right? But it is, our sun is even bigger. Alpha Centauri is comparable to the sun, very similar in a lot of ways, as well as the sizes you could see. Okay. And then we have Vega, Procyon. Procyon is a Well, on our reference table, it's a dead star, Procyon, and a small white dwarf, but bigger than our sun. Spica. A blue hot star, very big, and that is on our reference table, one of the biggest stars on our reference table. Even bigger than that is Aldebaran, okay, a giant red star, dying. Polaris is also a dying star, also called the North Star. And they are big. Arcturus, you could see sometimes in the nighttime sky. It's really big, it's really bright. You might think it's a planet, but it's actually a star, a dying star. Rigel, Deneb. And it just keeps going big. So if you want to just keep going, right? Look, then you can see nebula. There's so many different nebulae. And they're all like different sizes, some bigger than others. This one's called Stingray Nebula because it looks like a stingray. Gomez's hamburger, cat's eye. Looks like a special marble. It used to call it like a cat's eye marble. Hourglass Nebula. And this is after a supernova explosion left behind of a dead star, a star that was big and massive and exploded all of its guts and left behind. And from the cosmic dust and debris, new stars will form. Eskimo Nebula. The Horsehead Nebula, I had that in my classroom. Picture that. The Pillars of Creation. That's cool. That's in Orion's belt. And, you can have fun with that. So check it out. I got to go. My dog is barking. And peace out. See you next time.